So to get started, we need to start at the very beginning. And what more fundamental question can we ask other than, what is chemistry? Why should we be interested in chemistry? Why would we study it? Well, chemistry, in sort of the broadest overview, we say that it is the study of the composition, properties, and the transformations of matter. Well, as you can see, that's a pretty broad starting point. And we're going to break down what each of these things mean, again, on a very, very wide overview. But as you can imagine, this course and courses like it are just intended to give us a very, very broad overview of what chemistry is and why we would study it. So we can even start as basic as asking the question, what is matter? So matter is just material. Anything that takes up space or has a volume and has a mass. So now let's look at a couple of these other things, and we'll go sort of one by one. When we're talking about composition, what do we mean there? Well, we're talking about what is matter made of. Or what is any sample made of? What compounds make up the sample? What elements? How many? And all of these things matter, even how many of the element. One of the jokes some chemists will tell is, two friends went into a bar. The first one says, I'll have some H2O. And the second one says, I'll have some H2O too. So what happened to the second person? They died. Why? Well, if we take this as H2O and H2O2, we're talking about two compounds that are both made up of hydrogen and oxygen. The first one, of course, is water. But the second one is hydrogen peroxide, something you definitely don't want to drink. So the number of the element that you have matters, and the identity of the element matters. Another reason we might want to study chemistry is, let's look at the following. I always find these to be a great place to start in a course like this. So here's an ingredient list. So take a look at this. Is this something you'd want to consume? How about this one? This is an even longer list. very long list of chemicals here. You think it's something you'd want to consume? Well, both of these come from posters that are made by a chemistry teacher in Australia. And he basically labeled these as, what if we had to put ingredient lists on natural foods? Would you still want to eat them? And so that first one, those are just all the components you find that would make up a banana. Second one, those are the names of all the compounds you find in a coffee bean. So the identity of chemicals matter, but it's also important that we not, just be too worried about every name of every chemical, because it's always the quantity that matters. What about properties? Well, when we talk about both properties and transformations, we divide them up into physical as well as chemical. And it usually makes the most sense to talk about these together. So, physical properties are things such as color, shape, melting point, and they're properties that do not alter what the substance is. So, for example, if you melt ice, it was water before you melted it, it'll still be water after you melt it. You've changed the way it looks, but you haven't changed what it actually is. Same thing if you take a piece of paper and rip it apart. Again, have you changed the appearance? Yes. But have you changed the actual composition of the paper? The answer is no. And so that makes things like that physical properties or physical transformations. Chemical properties or chemical transformations have to do with the actual bonds within a molecule. So this could be things like rusting, combustion, acid-base reactions. Anything that physically changes the actual bonds within the molecule would be considered a chemical transformation. And any properties that arise from that we would consider to be a chemical change. Now, within chemistry, we have a lot of different subfields. So this is a general chemistry type course, which is just basically an overview of some of the basic concepts of chemistry. But beyond that, chemical disciplines are divided up into things such as organic, inorganic, analytical, biochemistry, physical chemistry, and environmental. And there are others as well, but these are sort of, we could say, the 6 main fields. What do each of these entail? Well, organic chemistry, for example, this focuses on carbon. Why carbon? So why do we have an entire field that studies what goes on with one element? Well, all of our life form is carbon-based. And pretty much everything we do on a daily basis is carbon-based. So life, fuels, polymers, pharmaceuticals. It's pretty much impossible to do, well, anything in life without running across organic molecules. Inorganic focuses primarily on metal-based compounds. Analytical chemistry looks at separation, identification, and quantification of samples. And this actually gets you well into the area of forensics. A lot of forensic chemistry is considered analytical chemistry. Biochemistry is exactly what it sounds like. It's biological. Same thing with environmental. This is studying the chemistry of the environment. And physical is the application of, or the sort of the intersection of physics and chemistry. So for many of you who are taking a course like this one, you won't really have much to do with most of these fields. But many of you, especially those of you in dietetics or within that area, you'll probably go on to take you may go on to take an organic course in the future, as well as possibly a biochemistry course. So next we want to talk about the scientific method. The scientific method is a systematic method that we can use for studying any process that's based on reproducibility. So in order to talk about the scientific method today, what we're going to do is sort of talk about the steps and also at the same time apply them to an example. And to do that example, we're going to pick on this guy a little bit. Who is it that we're going to pick on? Well, this is Justus von Liebig. And you can see he was around in the 1800s and a pretty important scientist. And you can see this even suggests that some people consider him to be the founder of the field of organic chemistry. And for me, as an organic chemist, there's no doubt that the stuff he did as an organic chemist was critically important. But we're going to pick on one of the things he got wrong. And one of the reasons I'm going to pick on this is because Not only is this something that he got wrong, but second, this is something we can easily disprove. But third, even though this is something that he talked about over 150 years ago, we still hear people getting it wrong today. And what is that? And that's the following. So in addition to other things that he did, Liebig got into chemistry involved with food and cooking. If you think about cooking, everything you do when you cook is all chemistry. And so Liebig advised that cooks should sear the meat initially to retain fluids. And so his idea that searing meat seals in the juices is widely believed, but turns out it's not at all true. And that's something that probably many of you are already aware of. But is that something that we could easily predict, or easily prove, or disprove? So we're going to talk here about the steps involved in the scientific method, and then look at some examples that how we could prove this. So the first step is always to make observations. And so we do that most of the time by performing experiments. So if we wanted to try and prove or disprove what Liebig said about cooking a steak, what could we do? Well, we could cook steaks in many different ways. So once we've done that, what would we do next? Well, from the experiments that we've done, we're going to start collecting data. And for our steak example, what we might do is eat each of the different steaks, or at least sample them, and see what do we like better, what don't we like. And so this allows us to form a hypothesis based on the data that we collected. And so the hypothesis that Liebig formed was that searing meat seals in the juices. All right, so now we've got a hypothesis. And we're going to continue to test the hypothesis. We do this by doing more experiments, collecting more data. So maybe we do this by cooking 2 steaks, and we'll do them to the same temperature. One seared, one not, and we'll measure the mass. So finally, that will give us a result where either our hypothesis fits and we can promote our hypothesis to a theory, or it doesn't fit and then we discard it entirely, or modify it. And so with our steak example here, we find if we do this, the seared steak actually loses more mass. So it's not even equal. It loses more mass, and that's because that searing happens at a very high temperature. It actually drives off more liquid. So why then, and so as a result, we've managed to disprove Liebig's hypothesis. So then why do we sear a steak? Well, we do it for an entirely different reason. And what is that reason? Well, we do it for something known as the Maillard reaction, which is a reaction between amino acids and sugars, and that's what gives the flavor. But why do we need to sear it? Well, typically, if we don't go to a high temperature, then this reaction doesn't necessarily occur. So finally, with this section, we need to talk about this term theory. Because this term theory is unfortunately one of the most abused terms in probably all the English language. You know, we often hear when people are trying to sort of downplay something that, you know, that's just a theory. But a theory is the best explanation based on all current evidence. And because of the way that science is defined, the way that we do science, a theory can be disproven. So you find an experiment that doesn't support it, in fact, completely goes against it, and then you have to throw the theory out. You can modify a theory, or you can support it. But just because of the way that our scientific method works, the way we define science, you can't ever prove a theory to 100%. And unfortunately, as you may see in the news or in any number of other sources, when people don't seem to like a scientific theory, one of the things they like to say is it's just a theory, it hasn't been proven. And in fact, it turns out that that theory is the best evidence that we have. In some cases, the theories that we have will never be disproven. So the next time you hear that it's just a theory, keep in mind that that actually means that it probably has a lot of evidence that backs it up.